Hello, class. Today we're going to talk about functions, and we've talked about functions before. The definition of a function is for every input, there is exactly one output. So an input cannot go to two different numbers. Two different inputs can go to the same number, and that's okay. But the characteristic of a function is that the input cannot repeat. So we have to be able to test for functions in many different ways. A function can be represented verbally, numerically, graphically, algebraically. Let's take a look at this in a table form, right? So we have an input of 2 and an input of 2. So you know that the input cannot repeat. So this would not be a function. If we look at a graph, we do what's called a vertical line test. So if you were to pass a vertical line anywhere through this graph, would you hit a point more than 1 point at a time? And the answer is no. So this graph passes the vertical line test. So this would be a function. Let's look at, this is called a mapping. These are the inputs. Another name for domain is input. That's the x value. And here we see this input, -1, is going to two different ranges or y's. So this would not be a function because of this -1 right here. Let's look at this table. Inputs, there are no repeats, so we are fine. I will let you look at example 2. I'm not going to stress on that too much. Pretty much if you have an equation, where you have a y squared, when you solve for y and you get a plus or a minus, can you see that for any x, you're going to have a plus value and a minus value? So that would not be a function. So do you think this would be a function? The answer is no. This is actually, if you graphed it, it would be a circle. And graphically, with a circle, you could pass a vertical line through that circle and you would hit in 2 points. So that is not a function. Do you think this is a function? The answer is yes. When you solve for y, you would just have an expression that looks a lot like this, and that is a function. So a little review on that. Here's a little historical note on Leonhard Euler. You pronounce that Euler. He is the mathematician that gave us function notation. So let's take a look at this. If we have an equation or a function, this is a function. How do you know it is a function? Well, for every value of x, you would get a particular value of y. You're not going to get two values of y for that. So this equation is a function. We're looking at this f of x, which is another name for y, is equal to 1 minus x squared. So what does this mean? F of -1. It doesn't mean multiplication. It means that we are going to substitute in a value of -1 for x squared. So let's move over here. If we have a function defined for us as 1 minus x squared, and we wanted to find the value of f of -1, that means we replace the x no matter how many times it occurs with a -1. And be careful, when you are squaring a negative number, you always want to keep that in parentheses. So -1 quantity squared is a +1. So the value of f of -1 would be 0. And I believe that you have done this before as well. You can look at those other examples. Here's another one. If g of x, g is just another name for a function, is equal to -x squared plus 4x plus 1, find each function value. G of 2 is going to be replaced wherever there's an x. And then we just do order of operations and find the value. What about g of t? Well, you just put the t in for x. And when we do that, we simplify to this, and we have a function g of t. and we can't put those together because those are not like terms. What about g of x plus 2? Well, now wherever you see an x in the function, we're going to put x plus 2. So I know it's in the beginning of the year, so let's remember that when you have a quantity squared, this isn't equal to x squared plus 4. This is equal to x plus 2 times x plus 2. Let's quickly go over here and look at that. X plus 2 quantity squared means x plus 2 times x plus 2. And we have a binomial times a binomial, so we need to FOIL or use the distributive property, however you like to call it. Same thing, x times x is x squared. Outer x times 2 is 2x. Inner 2 times x is 2x. And then the last 2 times 2 is 4. So we combine our like terms. We have x squared plus 4x plus 4. Little review there. It's not a bad thing to do. We have a minus in front of the whole thing because that's what the function is defined as. So we're going to have to distribute that negative to each term. Up here we had 4 times the quantity x plus 2. That's 4x plus 8. Now let's combine our like terms. We have a negative x squared, negative 4x plus 4x. They cancel. Negative 4 and a positive 9 would be a positive 5. Okay, piecewise defined functions. I think this will be the most challenging for us today. Let's evaluate the function when x equals -1, 0, and 1. So our function f of x is equal to this expression for all x less than 0, or it's equal to this expression for all x greater than or equal to 0. So this is called piecewise defined because there's 2 pieces to it. All right, so what would f of -1 be? Well, -1 falls into this top category, right? So we're going to put a -1 in for the x squared. -1 quantity squared is 1. 1 plus 1 is 2. So f of -1 is equal to 2. What about f of 0? Well, you have to see which functions do I use. Is 0 less than 0? No. Is 0 greater than or equal to 0? Yes. So we're going to use this expression and replace the x with 0. So 0 minus 1 is -1. So f of 0 is -1. And f of 1, again, look at these. These are your domains. Which domain does this fall? It falls into the bottom. So we use the bottom expression and replace the x with 1. 1 minus 1 is 0. So in a little bit, we are going to graph these, and that gets a little bit fun. All right, moving on to example 5. Finding values for which f of x is equal to 0. Finding the 0 of a function is a very important aspect that's used in all sorts of real-world situations. So if we have a function that's defined, however, f of x here is equal to -2x plus 10, when is this equal to 0? Well, it's pretty simple. You just set it equal to 0 and you solve it. So f of 5 would equal 0. That's called the 0 of the function. Well, if we have a quadratic, which means degree 2, then we have to remember, how do we solve quadratics? You could factor. I hope that looks familiar and is ringing some bells. Or you could use a quadratic formula. X is equal to -b plus the square root. Okay, you can look that up. It's in your book. So for quadratic, remember we could have 2 zeros. And graphically, a 0 of a function, we will see soon, is where it crosses the x-axis. What about this? Find values for which f of x is equal to g of x. All right, well, here's f of x. Here's g of x. Where are they equal? Well, we simply equal them to each other. Set them equal. Whenever you have a quadratic, which means degree 2, we have to get everything on one side, set equal to 0. Again, factor or use a quadratic formula to find your two zeros. And I'll let you follow along with example B as well. Okay, the domain of a function. This also can be a little tricky. I did think we talked about this somewhat in Algebra 2 last year. The two times when you have to be aware of the domain of a function is if you have a fraction, a rational expression with an x in the denominator, that denominator cannot be 0. So let's take a look at that. We have f of x is equal to 1 over x squared minus 4. And we know that x squared minus 4 cannot be 0, right? We cannot divide by 0. So then we have to go about saying, well, when is it equal to 0? So when is x squared minus 4 equals 0? And I'm just going to contradict myself. I said when we're solving quadratics, we always have to have everything on one side equal to 0, except when we have only one squared term, no regular x term. There's another way we can solve this. We could add the 4 over, and then we can square root both sides. We would have x is equal to, when you're solving an equation and you've square rooted both sides, you have to do the plus or minus out front, right? So if x is equal to 2, or if x is equal to negative 2, this guy's going to blow up. We can't have that. So we would say our domain is all real numbers except x cannot be equal to plus or minus 2. Or sometimes you don't even need to put all real numbers, it's assumed. Domain x cannot be equal to plus or minus 2. So we're remembering that the domain are the x values. All right, so here's example 1. When you have a rational expression, you have to worry about the domain. And the second case is when you have a square root, because we cannot take the square root of a negative number. So we have to make sure that x is greater than or equal to 0. And that one was pretty simple, right? There's our domain. Any x greater than or equal to 0, we could put a domain d colon. What about if we had something like f of x is equal to, this is an example 7, the square root of 4 minus 3x. What would be the domain of this function? Square root cannot be negative. So we have to say 4 minus 3x must be greater than or equal to 0. And then solve that inequality. Well, let's review it. Let's do it. Let's go minus 4. So I would have negative 3x is greater than or equal to negative 4. Divide both sides by negative 3. And remember that when you divide by a negative number, that flips the inequality sign. So we have x is less than or equal to 4/3. And that is your domain. What is the domain of this function? All x, such that x is less than or equal to 4/3. All right. One more little addition. What is the domain? It's the x's. So it would be negative 3, negative 1, 0, 2, and 4. You would just list those out. And go ahead and look through these. I think that you can remember that. And I think that, oh, wait a minute, sorry. Path of a baseball. Last example here. A batter hits a baseball at a point 3 feet above the ground at a velocity of 100 feet per second at an angle of 45 degrees. Here's the path of the baseball. F of x is the height of the ball. X is the horizontal distance. So if you were to graph it, it's going to look something like this. And if any of you have watched baseball or hit a baseball, you know the path is parabolic in nature. It looks like a parabola. Okay, the question is, will the baseball clear a 10-foot high fence located 300 feet from home plate? So 10 foot high, we want to know if this expression, when x is equal to 300, is this greater than 10? You can see that they put in 300 for x, they evaluated, and they got at 300 feet, the baseball is going to be 15 feet high. So the answer would be, yep, it will clear a 10-foot fence. All right, that's it. I will list your homework either in an email or on Blackboard. Good luck.